So the next section of the webinar, I would like to cover the difficulties that sometimes exist around measuring DPs in sort of at the higher frequency end, 4 kilohertz and above, and that does depend to some degree on the, particularly if it's an adult ear canal. So it's going to require a little bit of imagination, but I'd like to just run a couple of little videos now showing some experiments using a model that represents the ear canal. I'd like to start by just describing what we can see in this video here. So we've got a PC running a small application that is using a USB sound card plugged in on the left hand side there, and it's running like a sound level meter application, and at the bottom of the screen there's a waveform, and there we've got a microphone that's attached to kind of like a stick, so that we can move the microphone around and sample what the sound field is in different places. And you can see when I tap the end here, the waveform shows the noise that I'm just creating, and the VU meter that's displaying on the top of the screen there is displaying the decibels of the sound. And the reason we want to do this is so that we can use the microphone just to test the sound field. Now the next item, you're going to need a little bit of imagination here, but that is a loudspeaker that is representing the loudspeaker inside an OAE probe. Okay, so it's 10 times larger than a standard loudspeaker in a probe, and for reasons that will become clear in a minute. But it's essentially the same thing, and then we can use the microphone just to test what the sound field is around the loudspeaker. Now, normally the loudspeaker is inside the probe along with the microphone, and so we are restricted to measuring the sound that is present right next to the loudspeaker. But obviously with this setup we can explore what the sound field is around the probe rather than being restricted. So now I've started the sound playing out of the loudspeaker, and that's just a pure tone at a fairly low frequency, and you can see on the sound level meter screen there's the sine wave showing, and you can see the VU meter indicating the intensity of the sound. Now as I move the microphone away from the loudspeaker, the sound reduces, and it reduces quite rapidly. Okay, so there I am about 5 centimeters away, and that's about 10 centimeters away, and the sound level has already dropped off that you can barely see the waveform now. And there we are back at the loudspeaker. Now that is completely as expected, because the sound field from the loudspeaker is radiating out into space, and so the pressure wave is becoming highly dispersed. So we're measuring less pressure with the microphone. Now, this is where you start to need a bit more of the imagination, because what I'm going to do is I'm going to insert this probe into the ear canal. And obviously we've made the ear canal a good 10 times larger as well, so that this probe fits in. So now there's the probe loudspeaker inside the ear canal. And now we can explore what happens to the sound inside the ear canal coming from the loudspeaker. And so if we start with the microphone next to the speaker, as would be the normal case, there we are, there's the loud sound being presented by the loudspeaker at the ear canal, into the ear canal. And as we move the microphone away, so there we are, 5, we're 10 centimeters away now, the sound field remains pretty constant. Okay, so it's certainly not diminishing like it did before. And again, it's fairly intuitive, because basically rather than being able to radiate into a big space around the loudspeaker, we've constrained the sound pressure wave into a parallel tube. So the pressure wave is relatively constant along the entire length of the tube. gradually, as we get further away, the acoustic transparency of the material I've used for that ear canal begins to affect the pressure wave, and it begins to reduce. But essentially, we can say it's fairly constant along the entire length of the ear canal. That's great, isn't it? That's kind of exactly what we're after, really. So we put a sound in at one end, and the same sound ends up at the other end of the ear canal. So now for the final part of the jigsaw puzzle, and even more imagination required. So I've actually 3D printed a tympanic membrane here with a small hole in it, which allows us to put the microphone into the ear canal, kind of from the cochlear side of the middle ear side of the ear canal. But it allows us to explore the sound field now inside the ear canal with an eardrum in place. Okay, and you can see there we are. The microphone is right at the eardrum now, the tympanic membrane, and we've got a nice loud sound that's been produced, propagated down the ear canal from the probe loudspeaker. Now let's just see what happens as we move that microphone back towards the probe, which is essentially where the microphone normally is. Okay, so as we move the microphone towards where it would normally be, we notice that the sound field gets quieter and quieter to the extent that it's almost completely disappeared when the microphone is right next to the loudspeaker. Now we know that loudspeaker is producing the full-size sine wave that we want. It's just that actually at the probe we can't see any of it, even though it's present at the tympanic membrane. And the reason for that is because the sound wave has reflected off the tympanic membrane and has been cancelled out. And we'll come on to that in more detail. But just as a little reminder, you can see that if I take the probe out of the ear canal, the microphone clearly shows that the loudspeaker is still producing the sound when it's not in the ear canal. But when we pop it in the ear canal and it's the tympanic membrane is in place, I'm afraid the sound field at the probe is considerably diminished. Having watched the demonstration of how we can probe the sound field in a scaled up model of the ear canal, I'd like to just go a little bit deeper now into the physics of actually what's happening in the ear canal. And for that, I'd like to use a couple of little applications I've written just to show the pressure wave as it travels down the ear canal. Now, both of these applications are available for you to download. They're just simple executable files, single files that don't install anywhere. So just run them, and then when you've finished exploring them, just delete them off your hard disk. There's no installation to undo. So here's a screenshot of the first one we will look at. And I'll just quickly go through which each of those panels, what they display, so that when I run the animation, you'll be able to understand what each of those windows is showing us. So at the beginning, we'll start with the ear canals displayed on the left-hand side, and the top pane with the red waveform is the pressure wave as it has been produced by the probe loudspeaker. And approximately in the middle, you'll see a purple vertical line, and that is the position of the eardrum. Now, we can experiment with that position, and that just enables us to represent different size ear canals or different wavelengths of sound, as it were. And along the top, you'll see I've marked quarter, a half, and 3/4, and those are the positions of the quarter, half, and 3/4 wavelength of the particular frequency of sound that I'm displaying in this chart. On the right-hand side, the red line shows the sound that has gone through the eardrum into the middle ear, and you'll see that there's a green dashed line on each of the diagrams, which is the amplitude of the pressure wave at any one point. So I think now if we just run the live animation, and you'll get a feel for exactly what it shows. So now you can see the waveform propagating through the eardrum, and there's a slider at the very right hand side of the application, and that's the absorbance of the eardrum. And obviously if the eardrum is letting all of the sound through, the middle ear is absorbing all of the sound, then you can see that the wave is propagating all the way through the eardrum, and absolutely none of it is being reflected back. So the blue line in the panel, the middle panel, shows the degree of sound that is being reflected back from the eardrum. And by changing the slider at the far right, we can alter the amount of sound that is being reflected. Once we do that, and the absorption is no longer 100%, some of the sound is being reflected back down the ear canal rather than transmitting through to the middle ear. And that waveform is the blue waveform, and it occurs at exactly the same time as the red incoming waveform, and so the two waves add together. And so at the bottom panel, where we display in a kind of purple color, that is the combined pressure wave of the incoming sound plus the reflected sound that has come back from the eardrum. Now, the important thing to look at here is to note that the dotted green, or the dashed green line, which shows the pressure wave, the actual pressure at any point in the ear canal as that wave propagates, you can see that actually at the probe end, the far left hand side, it no longer shows the full amplitude of the waveform. So we're in a kind of null in the sound field there, caused by the destructive interference of the reflected wave. So recalling what we saw with the microphone in the plastic ear canal, you can see why now that at the probe loudspeaker the sound field had gone to almost zero, and that's because the pressure wave that was reflected back at exactly that right wavelength cancelled out the incoming sound. So what we can see in this is that the amplitude of the pressure at the eardrum is actually high, but at the probe we can't measure it. We're in a null in the sound field, and that makes it very difficult for us to estimate what the sound level is at the eardrum. Given that the length of the ear canal relative to the wavelength of the sound has such a critical influence on whether the sound field is cancelled out at the probe, we obviously have a very different effect of this cancellation across frequency. And so the next piece of software I'd like to show you is the frequency domain effect of this cancellation. And this will look rather familiar now in terms of when we look at probe fit spectra, when we're fitting the probe in the ear. So again, I'll just start by introducing the various aspects of this software before I run the animation. So in the top left, we have a panel that shows the probe fitted into an ear canal. And there's a little slider just underneath the ear canal, and that enables us to change the dimensions of the ear canal. So we're fitting that probe into adult, child, or infant ear by moving that slider around. Then on the top right, we have two green bars, and the green bar on the left shows the level of the sound measured at the probe, and the green vertical bar on the right shows the level of sound actually at the eardrum. And then the panel on the bottom right is the one that will be familiar to us from when we're fitting the probe using typical OAE software. And this is a chart showing the spectral energy of the stimulus as the probe is fitted in the ear canal. And there are two lines on there. The red line shows the level of the energy density at the spectrum at the tympanic membrane, the eardrum, and the blue line shows what is actually measured at the probe. So now I'll just run the animation and you can watch the effect of the change in ear canal. So now we're running the animation, and first thing, the green bars that indicate the signal level is at a particular frequency, and the slider at the bottom of the spectrum there, we can change the frequency. So now I'm changing the size of the ear canal, and as I do that, you'll notice the blue line in the spectrum at the bottom is changing quite dramatically, and as I get to a very small ear canal, the probe spectrum is exactly the same as the eardrum spectrum, but as I move the slider to make the eardrum bigger, then you see this resonance effect at 3, 4, 5 kilohertz and moving in frequency depending on the length of the ear canal. The green bars, which show the relative levels of the stimulus at the probe versus the stimulus at the eardrum, by selecting a frequency with the slider at the bottom, the very bottom right hand side, you can observe what's happening at the eardrum versus what is happening at the probe microphone. And you can see that if you set the level to be constant at the probe microphone, the level at the eardrum changes significantly as the size of the ear canal is varied. So let's think about what the practical implications of what we've just seen there. The TE is a broadband stimulus, and we use automatic gain control when the probe is inserted into the ear canal. Often the stimulus level is then adjusted using a peak level adjustment, and with no attempt is made to adjust the shape of the stimulus to correct for any frequency responses found in the ear canal. So it's just simply a level adjustment. And so the stimulus is not adjusted, but the outward emission response is not affected in the same way by these ear canal resonances, because the wave is only traveling one way towards the microphone. And so in general, in TEs, there's not a large impact in the clinic for these kind of problems. For DPs, the situation is different, and it depends upon the ear canal size, as you've just seen. So for infants, in general, particularly with neonates, it's unlikely that the resonance issue becomes a problem up to 6 or even 8 kilohertz. With adults, it definitely gets more complicated, and the secret is to obtain a good deep insertion of the probe, if possible, and to look at the probe fit spectrum as you're fitting the probe, because there are telltale signs of an ear canal resonance, which is you see a notch in the spectrum that moves as you insert the probe more or less deeply. Now, if it's present and you can't make it go away with a better insertion, then you just need to be mindful of the fact that the stimulus level may not be as exact close to the target stimulus level as we had hoped. And the main thing to be aware of is that if you are performing a repeat measurement, so if you're monitoring for noise-induced hearing loss over time or ototoxic medication, etc., the main thing is to ensure that the fit is repeatable between measurements. So again, if you have a patient come back in after 3 months, pull up the old notes, have a look at the probe fit, and just try and reproduce that fit when you insert the probe, so that at least we're kind of controlling for one of the variables if we can. And I will just finish this section by saying that many manufacturers are acutely aware of the issues around this, and they're all tackle it in different ways to try and optimize things for you. And there's no doubt about it that on the horizon there are new techniques, forward pressure, emitted pressure, etc., which will slowly appear on clinical instruments in the years to come.